Hello, welcome to London Bernoulli. Next week it's going to be Oliver Nash, who's going to tell us about Lie algebras. But this week we're very pleased to have Ashvni Narayanan from the London School of Geometry and Number Theory here in London, who's going to tell us about p-adic measure theory in Lie.
Thank you, Kevin. Hello, everyone. So this is a project I've been working on for about 6 months now. I thought I'll complete it in 3 months, but I'm just maybe halfway through. So that's just how lean is sometimes. Anyway, because it's such a big project, I will not be able to cover everything. So what I'm going to be doing is I'll first give you an overview mathematically what p-adic functions are. And then I'll tell you how it's implemented in lean, and last, what's left to be done. Okay, so to begin with, just some basics about locally constant functions. A function is called locally constant if the preimage of any set in the range is open in the domain. And this is how it's defined in lean. It's pretty straightforward. You have the predicate is locally constant, and then you bundle it to make locally constant, which is a structure. And these are all continuous functions just by definition. And I'll be using this notation LC of XY periodically. Okay. So an example of locally constant functions are something called characteristic functions, which are essentially you take a set and you say the function is 1 on the set and 0 otherwise. That's a characteristic function. And for clopin sets, which are closed and open sets, it turns out that these functions are in fact locally constant. So that works well, and we'll be using that a lot. Another tool we'll be using will be the p-adic integers. So there are several different ways to characterize them. One of them is the obvious: you take the p-adic valuation and you complete the integers with respect to that. You get the p-adic integers. Or you can think of, again, look at the p-adic valuation, that gives you a p-adic norm. Whenever that is less than or equal to 1, all those elements are p-adic integers. And the most important way for this project, at least, is to think of them as a profinite completion, or as an inverse limit of z mod p power n z. So what this does is it gives us surjective map from zp to every z mod p power n z, which essentially takes an element in zp to its modulus p power n. And lastly, you can also think of it, this is just for, a better mental picture, as elements of the form summation ai p power I, where ai come from the z mod p power I z. And yeah. Okay, so here are some properties of zp. Because it's a projective limit or an inverse limit, it is compact, Hausdorff, and totally disconnected. In lean profinite spaces, I think that project was under construction, where profinite spaces, which are defined as compact, Hausdorff, and totally disconnected, was being connected to inverse limits, because these spaces can also be thought of as profinite limits. I don't know if that is complete. So I mean, it was another thing to show that ZP is a profinite space, while it is known that it has a projective limit. Indeed. Another non-trivial fact is that because ZP is a profinite space, it has, because ZP is a profinite space, it has a topological basis of clopin sets. In general, as we will see later, any locally compact Hausdorff totally disconnected space has a topological basis of clopin sets. But more specifically for the p-adic integers, these Clopin sets over here, which are essentially the pre-images of all the surjective maps to Z mod pow, the pre-images of the singletons in it. These sets are Clopin and they form a topological basis. Okay, just some notation. We'll use chi NA for all the characteristic functions corresponding to these UNAs, and these are all locally constant functions. And the special property is that, in fact, they linearly span the set of the space of locally constant functions from ZP to A, where, apologies, I forgot to mention what A is. I think A is a commutative ring. So you can write any function, any locally constant function f as summation f of a chi NA for finitely many n's. And in fact, there is a specific n such that you can think of it as partitioned over these sets UNA for this specific n. Okay. Similarly, you can do the same thing just by adding a Z mod DZ, where D is co-prime to P, and you'll get the same result because these Z mod DZs are discrete topological spaces, so everything just works out fine. Okay, now getting to the interesting part. What is a p-adic measure? To define a p-adic measure, we need to define something called a p-adic distribution, which is essentially an A-linear map from the space of locally constant functions to A. I need A to be a normed ring here. Well, I think you can make this definition more generally, but for the following, I mean, the properties that are going to follow, I need the space X to be profinite and the space A to be a normed ring. So then a p-adic measure is essentially a bounded distribution, which is you look at the norm of F under a p-adic distribution phi, and if there is a K such that norm of phi of F is less than or equal to K times norm of F, then that is a p-adic measure. And as Kevin pointed out a few days ago, this condition that K is positive is actually not needed. It's just redundant. Okay. And here is an example of a measure, which is the Bernoulli measure on these characteristic functions chi NA. It's defined to be this thing where these brackets are the fractional part. And although this looks a bit random, this actually comes from something called the Bernoulli polynomial. Sorry, I haven't mentioned it here, but I don't know if I can write it down. This is essentially B1 of A by B bar n plus 1 minus C times B1 of C inverse A by B bar n plus 1. And I'm told that there are reasons for this, but I haven't been able to decipher them yet. In any case, you can replace these B1s with BIs in general, and you still get a measure. So these are all the Bernoulli measures. And well, they're technically defined using the UNAs, but then there is a bijection, a correlation between the chi NAs and the UNAs. So it's the same thing. Okay. Oh, sorry, I don't think anybody could see what I wrote down. I'm sorry about that. Okay, never mind. Okay. Okay, cool. So that's what the p-adic measures are. And we are going to be working specifically with the Bernoulli measure. So why do you want these measures? You use it to do p-adic integration. Specifically, you take a measure and you take a locally constant function f, then you can define the integral with respect to this measure to simply be its evaluation, mu of f. Very easy, it's linear, it's nice. And the best part about this is you can actually extend it to the space of continuous functions because the space of locally constant functions is dense. This is true when X is profinite and when A is a normed ring. So you can do this, and this is actually a linear continuous map. Finally, coming to p-adic L functions. Traditionally, p-adic L functions come from something called the Dirichlet L functions. And these functions just arise from this. These are just functions that take special values at negative integers in terms of Bernoulli numbers. And you just continuously extend them, analytically extend them to CP, to C. Similarly, the Kubota-Leopold p-adic L function is another meromorphic function that extends these negative integers over to CP, CP. And it has a pole at S equal to 1. So this chi over here is a primitive Dirichlet character. We'll possibly come to that later. And omega is the Teichmuller character. And the Teichmuller character just takes any element of the p-adic integers to a unique p minus first root of unity, which is congruent to that element, mod p. Okay, so that's a lot of jargon. What do we do with this? Essentially, you get this theorem, which is given in Washington. My reference for all of this work is Washington's Introduction to Cyclotomic Fields. And this theorem says that if you have a primitive Dirichlet character with conductor d times p power m, and s to be a p-adic integer, then this specific integral over here is some constant times LP of minus s chi. And this was helpful for several reasons, because when I started working on this project, CP did not exist in Lean. So essentially making sums and analytically extending would have been very problematic. Hence,
does it exist now?
I'm not sure.
I'm not entirely convinced it does.
Yeah, possibly not. But yeah, for various reasons, the correct space to have done this in would have been CP. Since that did not exist, I thought this would be a better alternative definition. And so that's what we work with. Because Z mod DZ and ZP are compact Hausdorff totally disconnected, the product of their unit spaces is also profinite. And so this thing works out very well. Of course, there is a certain problem with this. The problem being this is dependent on your choice of C, which is an integer that is co-prime to D and P. But I mean, it is to be shown that this is actually independent of C. Okay, so how is this done in Lean? Sorry, let me just have a look at the time. Okay, sure. So, yeah, how is this done in Lean? I'm just going to go through some specific points that were problematic and required ironing out. The first thing that required ironing out was this structure, topological structure on CXA. If you look at Lean's MATLAB for continuous functions, you will see that things are very well done for the algebraic structures on CXA. The topological structures, however, are a bit hazy because in general, you have the compact open topology, which is defined for C alpha beta, where alpha and beta are just any topological spaces. But over here, you're actually looking at something more specific, because whenever you have a compact space alpha and a metric space beta, this space is actually equivalent to the space of bounded continuous functions from alpha to beta. And so in some recent work done by Oliver, I guess he'll be talking about it next week, a proper structure was given to the bounded continuous functions that was used to get an induced structure on the space of continuous functions. But then the structure I wanted to work with was the subnorm structure, where the norm of f is defined to be the supremum of the norm of f of x, where x is overall elements of x. And so this had to be induced from the bounded continuous functions, and we had to show that both of them give the same thing. So that has been done, and I think it's almost in MATLAB as well. Okay. Next thing, there was a lot of work that needed to be done on the p-adic integers and its properties. So like I told you before, I wanted to show that ZP has a topological basis of Clopin sets, but more generally, it turns out this is true for any locally compact Hausdorff totally disconnected space. And we have this theorem here. The proof is relatively simple. The only problem that comes is when you have coercions, when you have to deal with coercions, because it was difficult to identify subsets of subsets as subsets of the main set, if that makes sense. So it gets hard to work with openness and closedness of all of this. That was the main difficulty. And if anyone knows how to do it using filters, then that would be great, because the proof is still 50 lines long, I think, even though it is in MATLAB. So it would be lovely to have something shorter. Okay. And as a consequence, I also found out that every locally compact Hausdorff space is totally disconnected if and only if it is totally separated. Whatever these things mean, I'm not going to go into that. Also, I want to highlight another point. When it comes to the space of continuous functions, all the work I did was actually for X non-empty in the beginning, because whenever you use sup, certain lemmas require your space to be non-empty. But then after a while, most very recently, you can also do it for X empty. So that works out well for all X. Okay, so like I told you, a lot of lemmas had to be made connecting the p-adic integers with Z mod p power nz. In particular, I had to work with 3 maps constantly. There was val, which takes an element of Z mod nz to a natural number, essentially the smallest positive number in the equivalence class. There is cast, which takes Z mod nz to any ring. But this cast, unfortunately, most of its properties only work when, it's a homomorphism and nice only when the characteristic of the ring divides n. However, this is actually not true, because it works pretty well for the natural numbers and integers as well. So a lot of those extensions have to be done. And finally, there is 2Z mod power, which we already spoke about, that arises from the projective limit. These are all surjective maps. Oh, sorry, 2Z mod power is surjective for every n. Okay, so like I told you before, we wanted to show that those specific sets, which are the inverse images of these singletons, formed a Clopin basis for the p-adic integers. And so I defined that to be something called Clopin from NA. And yeah, this came after a while because the thing that was defined first was this thing called Clopin basis that you can see over here. And you see it has there exists N and there exists an A, which was very difficult to work with because you have to keep using classical.sum and classical.sum spec. And so after a while, it struck me that a Clopin from is a better definition to make, and then just going from there. Okay, so the major theorem then is that these actually form a topological basis, and the proof was fine. It's not that hard, except you keep seeing these coercions from Z mod P par NZ to ZP and ZP to Z mod P par NZ. And these coercions occur from val and the maps that I told you about before, cast and val. And unfortunately, if you start with something in Z mod P par NZ, you go to ZP and then come back down to Z mod P par NZ, or the other way around. Those things may not be equal. Moreover, most of these properties did not exist in Lean. So with time, now hopefully they will be PR'd soon. But yeah, the basic fact that was used was that this set, which is the pre-image, is actually a ball centered at A with radius P par minus N. And in fact, this set is Clopin, like I told you before. Okay. Yeah. So how does that link to the integral? What it does is it helps you give a dense inducing map for this map from the local space of locally constant functions to the space of continuous functions, which was initially just injective, but it has dense range because of that property, and the induced topology is the same. Hence, you can extend the integral very nicely because every time you have a dense inducing map, you can actually do a lot of nice things because extension properties become very simple. You just need to restrict to the base case of the locally constant functions, and everything works very well there. So we end up with this definition of the integral, which is true for a profinite space, X a profinite space, and A a normed commutative complete ring, which is just extending the evaluation map phi. Oh, I'm sorry, I don't think I wrote down the definition of a measure, but it's essentially just a linear map that from the locally constant functions to A, which is bounded. Okay. Moreover, another important property which follows from the boundedness of the measure is the uniform continuity of phi, which was used throughout. Okay. And so that gives us the definition of the integral. But that's just half the story, because it was really hard to show that the Bernoulli measure is actually non-empty.
What do you mean by non-empty?
As in, it has some element, as in the set of measures has some element, which is, I chose to be the Bernoulli measure, apart from the obvious zero measure. Yeah, that was a big pain. But yeah, so coming to Bernoulli measures, we defined them on characteristic functions, and we wanted to extend them to all locally constant functions to make it a measure. And so to do that, because we work with locally constant functions in the unit space, first you need to extend them to the entire space, which is just done by taking it to be zero on all non-units. This thankfully turns out to be a locally constant function, so things worked out well. And then how do you actually define EC of f for any locally constant function f? There were several different ways to do it. the way I chose was to look at the sequence Gn, which is essentially the sum of f of a with EC of chi Na. So what you should think about over here is you can think of the locally constant function as for some n being equal to summation of f of a for each of the points a in z mod p power nz. And so that characteristic function chi na is essentially just replaced with EC of chi na. So it would make sense that this thing somehow converges to f, and so that would give you a good linear definition of EC of f, as in it makes the measure linear. Okay, so then I wanted to show that this is eventually constant, and it suffices to show that you can find some n for which for all m bigger than n, gm is the same as gm plus 1. And how we did that was using discrete quotients. So we basically defined a function capital F, which takes a natural number n and returns a discrete quotient. Oh, by the way, every locally constant function gives rise to a discrete quotient, which is basically x is related to y if and only if fx equals fy. That gives you a disjoint cover of the domain. And so you define x is related to y with respect to capital F at a value n if and only if x mod d is equal to y mod d and x mod p power n is equal to y mod p power n. Okay, so how this helps me is it gives me that n that I need to show that g is actually eventually constant. And so one of the big three lemmas was this lemma factor f, which says that you can actually find an n for which this discrete quotient over here leads to a refinement of f, meaning that for this n, f of x is equal to f of y, wherever capital of f of x is equal to capital F of y. I'll give you a moment to digest that.
So it's some sort of uniformly continuous statement.
It's just a discrete quotient.
The point is that n is independent of x, isn't it?
Yeah, exactly. Okay, so basically what we've then done is shown that you can find some n, after which if I look at summation f of a for a in z mod p power nz, or summation f of a for a in z mod p power n plus 1z, these two sums are the same thing. And that's exactly what we needed. So yeah, this is another big lemma. I just wanted to point out over here that we had to define this set called equiclass m dot suc, which essentially is the set of all y in z mod p power mz, m plus 1z, which is congruent to a certain x in z mod p power mz. So it's the lift of z mod of a singleton x in z mod p power mz to z mod p power m plus 1z. Okay. And so once you have that thing, you can factor out all the f's, and all you want to show is that the summation of EC over this equiclass is the same as EC over the original point B. And that was not too bad to show. I mean, the proof is really long. Each of these proofs is 50 plus lines. I'm hoping to reduce the length of it, but yeah. So it's here. And in fact, over here is where I needed my space A, I think, to be a Q algebra. I did not need anything like that before this. And combining it with the fact that ZP needs to inject into it, finally, I need my space A to be a QP algebra. Okay. So that shows that Gn is eventually constant. Finally, another challenge was to show that the units map is continuous, because you actually want your, remember that the integral chi omega inverse A par S, you want that to be a continuous map. So you want this map COI from unit ZP to ZP to be continuous. And a point to note over here is that the topology on the units of ZP is not arising from ZP. It's in fact something called embed product. And this is done well because I think you want this map to coincide with the induced topology only when inversion is continuous, which is true for topological groups. And since ZP is a topological group, that worked out well. In fact, what is true is this map COI for ZP is actually an open map and a closed map. So it's an embedding. Yeah. Okay, so finally coming to the p-adic L function, we made some small tweaks to it, thanks to Kevin. Instead of using the variable S, which was originally taken from ZP and in fact from CP, like I told you, since CP does not exist, we chose to work with W, the variable W, from the weight space, where the weight space is essentially just a continuous monoid a continuous multiplicative homomorphism. And what needs to be shown then is that these elements of weight space actually correspond to these elements coming from ZP. So the correspondence, I think, is over ZP, you have A par S, where each S in ZP is corresponding to something in the weight space. That is non-trivial, I think, and remains to be proved. Yeah, but modulo that, we finally can define LP of W chi to be this integral over this constant, except this constant over here need not be a unit because it's not. But because we are working in an algebra, I can actually look at, and I think this comes from the base ring, I can actually divide over by it, which was nice. The only problematic part is when W is corresponding to S equal to 1, because we have a pole over there. So that's what is the difficult part, but otherwise, finally, this thing exists in Lean. So what's the point of this definition? Well, to be honest, currently, it's not really worth anything. I did not use anything about chi being a primitive Dirichlet character or functions of the Teichmuller character or properties of the weight space. All of these things will come in to show what the p-adic L function was actually defined for. That is the specific values it takes on the negative integers. And that's a project that is still heavily under construction. But yeah, these things are done. And currently this code is possibly around 3,000 lines long because a lot of these proofs are really, really big. And yeah, so some future directions. One is to show that the p-adic L function takes those special values at the negative integers. That turns out to be equivalent to showing that the p-adic L function is actually independent of C. But all of this can be done only when we can give that correspondence between the variable S and the variable W coming from the weight space. Okay, And I think p-adic measure theory is a very cool tool. I think it may actually have some correspondences with some things from normal measure theory, because if I'm not wrong, you can probably make a sigma algebra from Clopen sets, which will lead to rather interesting results. So that needs to be looked into. And that's it. All of my code is available on the p-adic branch in case anyone wants to have a look. It is not very well done. A lot of definitions do not have doc strings. You can feel free to blame me for that. The linter is very, very unhappy. And finally, I would like to thank everyone in the Lean community, because like you saw, I had to use results from algebra, topology, analysis, a lot of spaces. Would have been very difficult to do this without that. And that's it.
Thank you very much. I shall stop the recording. Maybe jump on this machine.